Welcome to this video on determinate structures. It is one of several videos in a short course on equilibrium posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. The theme of this video is the analysis of determinate structures. But what is analysis? And what does determinate mean? And what is a structure in this context? To start with the last item, a structure in this context is a bridge, building, electrical power transmission tower, or any other structure comprised of longitudinal members. By longitudinal members we mean that one dimension of the member is much longer than the other two dimensions. That is indicated by the fact that all the structural members in the figures on this slide are drawn as a line. Each line is one structural member. It is possible to envision more complex structures with plates and shells, but those are not part of basic structural analysis. An implication of the present interpretation of structural members is that each member has a cross-section, such as the wide-flanged steel cross-section shown here. Please note that the longitudinal dimension of each structural member is generally much larger than the dimensions of the cross-section. Having established that general rule, we can further categorize each structural member, and as a result, each structure. For example, what is a truss relative to a frame? The answer is that truss members can take only axial force. Truss members cannot carry load by bending moment and shear force. This is a typical example of a truss structure. In contrast, beam members carry bending moment and shear force. A typical example is this continuous beam, which carries load placed along the member. A truss member could not carry this type of load. Trusses have all loads placed at the joints. Notice that this continuous beam has a hinge placed here, which means that there is no bending moment at this location. Next, we define frame members as those that can carry axial force and also bending moment and shear force. The distinction between beam and frame elements is not important, but oftentimes engineers work with continuous beams laid out horizontally with no axial force present. This portal frame is an example of a structure that consists of frame members. Finally, it is possible to mix truss and frame members. An example of such a mixed structure is this horizontal frame member, or beam, that is being held up by an inclined truss member. If you recall, we are in the process of introducing the analysis of determinate structures. We now ask what analysis is. Simply speaking, structural engineering is a back and forth between structural design and structural analysis. First, the engineer establishes a trial design. The trial design includes the length of all members, often including their cross-section dimensions. Next, the engineer carries out a structural analysis in order to determine the deformations and internal forces that are caused by external loads on the structure, such as wind and snow loads. In this course on equilibrium, we will not address the calculation of deformations. Rather, we are interested in determining certain diagrams for each member. These diagrams show the internal forces that are present inside each member, due to the external loads. In basic structural analysis, where we do not consider torsion, the diagrams we are seeking are the bending moment diagram, the shear force diagram, and the axial force diagram. The next slide visualizes those internal forces. Here is the bending moment inside a member, whose magnitude is drawn in a bending moment diagram. Here is the shear force inside a member, whose magnitude is drawn in a shear force diagram. Here is the axial force inside a member, whose magnitude is drawn in an axial force diagram. Notice that the symbols M, V, and N are often used for the bending moment, shear force, and axial force, respectively. Finally, we have arrived at the task of understanding what the word determinate means. The determinacy of a structure is important for how we analyze the structure, and it is also important for how the structure behaves. It is customary to express this concept as the degree of static indeterminacy. Formally, the degree of static indeterminacy is the number of unknown forces in the structure minus the number of equilibrium equations. That means the degree of indeterminacy gives us the number of unknown forces in the structure that we are unable to determine with the available equilibrium equations. One implication is that a degree of static indeterminacy equal to 0 means that the structure is determinate. In other words, a 0 degree of indeterminacy means that we have a sufficient number of equilibrium equations available to determine all the internal forces in the structure. In this video, we consider only determinate structures. In another course on indeterminate structures, we get into the details of calculating the degree of indeterminacy for specific structures. That said, the next slide summarizes some important properties of determinate structures. As mentioned already, equilibrium considerations are sufficient for determining all the internal forces in the structure caused by external loads. An implication of that is that there is no need to know anything about the properties of the material in the members in order to find the internal forces. More precisely, the stiffness of the structural members does not influence the distribution of forces in the structure. Another interesting point about determinate structures is that there will not be any additional forces in the members if the structure experiences support settlements or temperature changes. In other words, the supports can move and the members can change size without any additional forces inside the structure. On the downside, a determinate structure does not possess redundancy. That means that the structure will collapse if one member or one support is taken away. Informally speaking, some architects and engineers will prefer the relaxed nature of determinate structures, which never develop additional forces. Conversely, some engineers will prefer indeterminate structures because they possess redundancy and may therefore be safer if extreme loads occur. Conventions for drawing the diagrams that show the internal forces in a structure is an important and sometimes contentious issue in structural analysis. Unfortunately, a multitude of choices are viable. It is vital for the person reading, say, a bending moment diagram that the convention is clear. First, let us be clear on the fundamental and general fact that all these diagrams are drawn along each member, showing what occurs inside the member. Next, we need to establish a convention for drawing axial force diagrams. Is tension positive or negative? For bending moment diagrams, do we use signs, or do we just draw the diagram on a specified side of the member? For shear force diagrams, do we use signs or do we draw the diagram on a specified side of the member? The next slide shows the choices made in terje's Toolbox. The choices are visualized for this simply supported beam with uniformly distributed load. Bending moment diagrams are drawn on the tension side without any signs. Some engineers use signs and say that a positive moment means tension at the bottom, but that rule does not work in general, for example for frames with vertical members. Next, shear force diagrams are drawn on either side of the member, but marked with a sign that indicates whether the shear force is clockwise, which is positive, or counterclockwise, which is negative. Finally, axial force diagrams are drawn on either side of the member, but marked with a plus sign where the axial force is tension and a minus sign where the axial force is in compression. The next slide shows the procedure for analyzing determinate truss structures. Examples that utilize this procedure are provided in other videos. First, it is necessary to determine the reaction forces. To do so, we consider the global structure as one rigid body, employing equilibrium in the horizontal and vertical directions, as well as moment equilibrium. With those three equilibrium equations, we can determine up to 3 reaction forces. We saw it in the video on the equilibrium of rigid bodies. For the truss shown in this slide, there are exactly 3 possible reaction forces, so this is looking good so far. Next, we select an arbitrary joint with maximum 2 unknown forces. One possible choice is the rightmost joint of this truss. The horizontal truss member and the inclined truss member coming into this joint are the 2 unknown forces. Next, we use knowledge from the video on the equilibrium of forces at a point to determine the unknown forces in those members. The procedure continues from joint to joint until the axial force in all truss members is determined. For beams and frames, we also start by using global equilibrium equations for the structure to determine the reaction forces at the supports. What is done next will vary from instructor to instructor. Some start with the shear force, and a subsequent slide on beam equations will explain why that is a viable approach. However, in this video, the bending moment value at selected locations is determined first. That is easy to do, because the structure is determinate and a bending moment is simply force times arm. Other videos will show examples for beams and frames. Once we have the bending moment value at key locations, we simply draw the bending moment diagram as a line between those known values. As shown in this table, if there is no distributed load along the member, then the bending moment diagram is just a straight line. The upcoming beam equations will explain why. Similarly, if there is uniformly distributed load along the member, then the bending moment diagram is a parabola. The examples covered in other videos will explain how to get the shear force diagram from the bending moment diagram, and how to get the axial force diagram from the shear force diagram. Conducting structural analysis in this manner is helpful for advanced structural analysis methods, which give the end moments of the members as the primary result. However, be aware of the possibility of starting with the shear force diagram and then obtaining the bending moment diagram. The beam equations on the next slide explains the background. For this short course on equilibrium, this slide contains material from Euler-Bernoulli beam theory that is too advanced for us at this time. The figure shows equilibrium equations on the left-hand side, a kinematic compatibility equation on the right-hand side, and the material law of Robert Hooke at the bottom. When we cover beam theory, there are several interesting points here, including the differential equation for beam bending at the top. In this video, we want to focus in on the equation that says that the shear force at some point along a beam equals the derivative of the bending moment diagram at that point. This matches the observation we made in the video on equilibrium of a rigid body, where we found that the shear force is the change in bending moment divided by the length. When the length of the beam segment is infinitesimally small, we obtain this formula. The formula says that we obtain the shear force as the derivative of the bending moment diagram. It also says that the bending moment diagram is the integral of the shear force diagram. This explains the two alternative approaches mentioned in the previous slide. The next slide visualizes the path from shear force diagram to bending moment diagram for a cantilevered beam that is fixed on the right-hand side. The beam is subjected to a constant distributed load, and the x-axis has its origin on the left-hand side, as shown here. At first, we obtain the shear by integrating the distributed load. We do that because one equation on the previous slide said that the distributed load is the derivative of the shear force, neglecting the sign in this conceptual demonstration. Next, the shear force is integrated to obtain the bending moment diagram. This approach of obtaining the bending moment diagram as a mathematical function of the variable x is not adopted in terje's Toolbox. Some viewers might ask whether that will cause problems in advanced methods, such as virtual work to obtain deformations, where moment diagrams need to be integrated. The answer is no, because modern textbooks have formulas for integrating all kinds of moment diagram shapes. Working with functions of x for realistic beam and frame structures would be quite cumbersome in comparison with that approach. Nonetheless, we see on this slide that we found reasonable values for the shear force and bending moment in this beam. If we look at the values at the right-hand side base of the beam, we find that Q times L makes sense as a shear force value. That is because Q times L is the total load on the beam. Also, the viewer who is already familiar with structural analysis will see that QL squared over 2 is exactly the bending moment we expect at the base of a cantilever with uniformly distributed load. That concludes our exposure to the path from shear force to bending moment diagrams. We will establish bending moment diagrams first, and we will do that for a variety of frames and continuous beams. When we are doing that, it often saves time to be aware of the basic cantilevered and simply supported beam cases shown on this slide. Notice, the bending moment at the base of a cantilever with uniformly distributed load is QL squared over 2. The bending moment at the middle of a simply supported beam with uniformly distributed load is QL squared over 8. Many engineers will use that formula a lot, because it is the largest moment that can appear in a continuous beam, except cantilevers. For a point load P, the comparable values are P times L for the cantilever and PL over 4 for the simply supported beam. The next slide shows examples of when it is useful to simply adopt those formulas from the previous slide. Specifically, we can often circumvent the step of finding the support reactions first. It is always safe to find the reaction forces first, but sometimes life is easier because of the previously mentioned formulas and we may want to save time. Consider this continuous beam. We obtain the bending moment at the roller support simply by multiplying the load value by the length of the cantilever. The rest of the diagram is simply a straight line between the supports because there is no load along the member. For the beam below, we recognize the portion that carries the distributed load as a simply supported beam, carried at the roller support on the right-hand side and carried by the adjacent beam at the hinge. For that reason, we already know that the bending moment of the beam that carries load to be the parabola seen earlier for the simply supported beam with uniformly distributed load. The remainder of this structure is essentially a cantilevered beam with a point load at the tip. That point load is the shear force at the end of the simply supported beam, namely Q times L over 2. The beam in the structure on the right-hand side is carried by a pinned support on the left-hand side and the inclined truss member near the right-hand side. That means we find the bending moment diagram for this beam in a manner similar to what we did for the first structure considered on this slide. The bending moment diagram for the cantilever is known from the previous slide. The bending moment diagram for the remainder is a parabola with amplitude QL squared over 8 drawn between the known moment values on the left and right. If you are interested in the axial force in the truss member, then one approach is to consider equilibrium of forces at a point where the truss member connects with the beam. More about such considerations in the examples posted adjacent to this video on the lectures page of terje.civil.ubc.ca Toolbox. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.